Okay, so as our next speaker, we have Aleksandra Faust, who is a staff research scientist at Google Brain Research, specializing in reinforcement learning and motion planning. Previously, she has held positions in the task and motion planning research in robotics at Google, machine learning for self-driving planning, controls in Waymo, and was a researcher at Sandia National Laboratories. She earned her doctorate in computer science from the University of New Mexico, master's from the University of Illinois Urbana-Champaign. Her research interests in general include learning for safe and scalable reinforcement learning, learning to learn, motion planning, decision making, and robot behavior. Personally, I've worked with Alexandra before on a project, and I've learned a lot from her, especially because she has a very unique research perspective on robotics, on safe learning and edge learning, etc., which not a lot of people do, since most people focus on algorithms. So here is Alexandra.
Thank you so much for the introduction, and thank you for having me here. Uh, this is going to be a research overview talk of our last couple of years, certain pieces of the research. But before we start with that, we're living in the midst of the global crisis, and that affects each one of us in a very, very differently and on a very personal level. And yet, at this moment in time, unites us through a shared experience that opens up a new opportunities that we wouldn't have otherwise. For example, me giving a talk here at this event. Uh, the so it's really an honor to meet all of you and connect with all of you. And I will start this talk with a little bit of the personal story. Sure. Indeed. So this is my picture of my grandmother and me and my cousins. And if you're wondering, this is me. And my grandmother was a wonderful lady. She was a seamstress. She had a business running out of our home, and yet she was never able to leave our home. And the reason is she was born with the mobility impairment, and she could not walk well. So every step that she made in her life was painful for her, and she just could never leave the house. So I grew up helping run little errands for her and so on, and I always sort of wondered whether there was something that can be done for her to make her life easier. Well, it turns out that she's not alone, and normally I go and give a talk and say, right now, today in the United States, there is 11 million people, or the entire New York City and Los Angeles, that cannot leave their home without some kind of assistive device. But in this moment with the COVID-19 that's kind of hitting us across the globe, this is true for everybody. So service robots that can bring food and groceries and deliveries to people that can't leave their home or shouldn't leave their homes, it's a really life-saving thing. And there are lots of technical complexities to get to that point, mostly coming from there's so many environments and variations and differences in spaces and how people move and so on, and the robots themselves. So the question is, how do we start tackling this problem at scale? So the problem at scale is, how do we get autonomy at scale in real world on real robots? And what I mean by real world, so here is an example of a robot this is a micro kitchen in Google, that is trying to go to the sink over there. And we just started, kind of did several rolls from same start and end position over 5 minutes. Now there's this guy with a cart here that kind of blocks the way, so robot needs to go turn on the left, avoid this person, and get to the sink. And this was not staged, just a matter of world changes before our eyes, and here is the janitor now that the robot needs to avoid. And that's the real world. That this is kind of what we're up against. Now this guy moves around, and the robot tries, realizes that, and changes. This is actually a fully learned reinforcement learning policy running on that robot. So the rest of the talk is going to be talking about the methods to get us running to this point. What I mean by real robots, robots come in all shapes or sizes, and their sensors, so what they can see, their dynamics, how they can move, and their bodies, so their geometries, determine what they can do, what they're inherently capable of doing. We cannot expect car to fly, for example, and so on. So any methods that we have needs to produce safe and feasible motion in the dynamic world. So the classic approach generally do not scale. And the classic approach contains of the pipeline of perception and SLAM that tells what's around the world. Then we have motion planning that comes in and produces a plan, and then that's being passed to a control that actually moves the robot. And the caveat with that is that integration is hard. It kind of makes sense. It's modular and everything else. However, this modular approach is really what's preventing the progress, because each layer does not know about the errors from the layer before. And then it's kind of acting on a partial information. So when we put in a new environment, we need to have whole new set of bugs to fix and hand tune and so on. And it's a very human in the loop heavy process. Biological system, on the other hand, kind of learn curriculum of skills, so to speak. Whatever we do, our inputs, we observe our world with our sensors, and outputs, we express ourselves through the motion in this case, remain the same. And the process inside, from where do I select my goals, or how do I command my motors and everything else, remains internal. So the question is, can we do something similar? We're looking at designing set of skills that you can build upon each other, keeping inputs and outputs of the system the same. So let's look at, again, biological systems. Evolution determines abilities of the system, and it adapts the system itself to the world and the skills that to the world and the environment and the tasks that system needs to perform, right? So if I don't need to fly, I won't have wings, for example. And then once we have the system defined, we go and experience the world. This is my daughter interacting with the world, learning to walk through trial and error. She was fine. Until we can learn to safely navigate and move around in the world. And then once we have some skill set, we practice it, we reflect on that experience, and we learn what we call intuition. We learn to predict, without actually doing it, what the world will look like under new conditions based on our previous experience. So that is generally we have evolution, we have the skill development, and we have intuition. So can we repeat similar process in the context of robot motion planning? So in order to do that, we need to ask ourselves what is the most basic navigation skill. And one would say, if we connect sensing and acting, and we can produce sequence of feasible actions to reach a nearby goal. So this is a fancy talk that says going from A to B, and that point A is where I'm now, and point B is somewhere nearby, and then just dealing with whatever happens this way, just our robot in the micro kitchen, right? That goal there is nearby. I don't need a map. I don't need to understand the big picture. I just need to get there and kind of deal with whatever happens there. So that's our basic skill. Once we have that skill set, well, we can start building upon it. So how do we do that? We do that through reinforcement learning. And if you're not familiar with reinforcement learning learns behaviors, learns actions that produce good long-term outcomes. And the idea is that the robot interacts with the world, and instead of having label and whatnot, at every time step, it observes a scalar reward, And the objective is to produce behavior that has that maximizes cumulative reward. So it has the long-term good outcome. So that means that the robots sometimes might be making shorter-term suboptimal decisions, or kind of getting some penalty early on in order to get a longer-term gain. So the way this works is that we have a robot and it has observations. The observations in this case are the LiDAR. The LiDAR is here. And we feed several of them, so it has a history on it, and that goes into learner. Action space in here are linear and angular velocity, so going directly. And we train it in a small, this is a map of the micro kitchen. It has some obstacles, there are couches here, and then robot basically runs around in this world and experiences it just like my daughter in that video a few slides ago. And the objective here is to reach the goal. However, and that's vanilla reinforcement learning. Neural net is here, you feed into the algorithm and it should work. However, the problem with this approach is that this reward is not that simple. There are some design choices that we need to make. Selecting reward is hard. If we only reward agent when it reaches the goal, then it's going to need to go and explore for a very long time before it actually gets somewhere. And that's not practical. And then the second design decision that we need to make is to decide the neural network architecture. And this is yet another thing that it's very trial and error and human in the loop process and so on. So the question here is, can we automate this process? Can we learn these rewards in neural network architectures that, using evolutionary algorithms, that can actually design a system, learning system that can learn this task? And just as an example, if you put a bad reward, this is kind of the behavior you get on the robot compared to the one we saw in the micro kitchen. So it's very sensitive to the reward. So the method that we use, call it Out-RL, it works in two steps. It first learns to evolve the reward that completes the task. And then once we have an appropriate reward, then it involves the neural network architecture to fit the reward. So here is how it works. We start training population of these agents, and each one of them has slightly different reward out of they're being sampled out of the bunch of possibilities. And then we train the agent and we do evaluation based on the task objective. And task objective here is we reached our destination or we did not. And then we mutate. We select basically a new generation based on the experiences and stuff that we kind of the outcomes between the evaluation and how these the rewards perform. We select the next reward and kind of keep repeating that loop until we find the best policy and the reward that makes that learning task tractable. So once we have our reward, we repeat similar process. So again, start population of agents. This time the reward is fixed. They're all being rewarded for the same thing. However, the neural network architecture, their brain, so to speak, changes. And again, we do the evaluation after each training loop. And this time we evaluate against the cumulative reward and we select the best policy and our neural network architecture. And that produces actually good behaviors. So this is illustration of the training environment. It's very simple, right? Just a robot running around, playing and so. And then it does a direct transfer, that train policy that puts on the robot in environment with humans, with dogs, right? With moving obstacles and so on. It's generally pretty robust here. Here you can even see I blocked the way and he realized that and recovers and goes back. Can even transfer to a different robot. The difference between these two is 100 pounds or 50 kilos in weight. So this one moves much faster. So we evaluated these compared to the classic approaches, so non-learn approaches. We also compared it with the learn baselines and behavior cloning and such that they're not reinforcement learning based, and against the vanilla reinforcement learning that does not use the kind of this automated reward search and so on. And the non-learn approaches, non-reinforcement learning approaches produce smooth trajectories. However, they're not robust to noise. Once they're put in a real environment and there's any sensor and whatnot, their behavior really deteriorates. And the reinforcement learning approach is, on the other hand, robust to noise. And because inherently in the training process, we're adding the noise and so on. However, it's very sensitive to the reward. So having this automated search for the reward is crucial. Okay. So then we say, okay, this works for a robot. That's nice. Does it work for other things as well? So we tested on 3 different reinforcement learning algorithms and on 4 environments. These are the Mujoko environments. They're standard benchmarks for the reinforcement learning task, and 3 different objectives. So the idea here is that if you're not familiar with these environments, the reward is given as kind of complex objective of, oh, I need to stand up and go in this distance and so on. And we call this multi-objective. What we really want in this environment, we want this humanoid to run as fast as possible. We want this humanoid to stand up and reach the height as high as possible. And these 2, again, to go and run fast as possible, so maximize the distance reached. And these are simple, they don't require lots of engineering and so on. So when I say simple objective or distance reached, this is what I mean. It's really what we want. And then multi-objective is this standard reward is given in the benchmarks that somebody spent time optimizing and finding just the right challenges that it's easy to make the learning tractable. And then we ask 3 things. We ask first, does this reward search help? And top part is the one reinforcement learning algorithm, DDPG. The bottom one is PPO. The green line is the baseline that are kind of published that people do. Blue one is we're tuning the hyperparameters of the reinforcement learning algorithm. And then the orange is learning the reward. And basically the conclusion here is that for very simple tasks, we have a similar behavior, so it does not make much sense to do it. However, for the humanoid task, it's more complex. We actually have a huge gain. And here is the video of that. This is our humanoid running with the learned rewards, and this is the baseline. It's actually very visibly big change in behavior. So the second thing that we ask here is, does it make sense to engineer this complex multi-objective function? So we do the cross-training. What we do for the cross-training is that, let's see. Here we evaluate the over task objective. This would be distance reached. And then the standard reward is this complex multi-objective function that somebody spent training. So the light red line here means that this guy was trained on this standard objective and it's evaluated on the same thing. The dark green one is trained using maximizing this simple objective, which is the distance reached, and then evaluated that performance on the standard objective. And this is the delta between their performance. This is the same thing on a different algorithm. So this is soft actor critic and this is PPL. So this means that Somebody spending time to hand engineer painfully this complex reward gives us very negligent performance in a very complex environment. There's a little bit more performance delta here, but it's not huge. So simple objective perform almost as well without hand engineering, so probably we shouldn't do it. So the third question we ask, so if I have fixed training budget, should I do hyperparameter tuning or the reward search? So for that, to evaluate that, we take number of population of agents and then we sort them in the order, basically in producing the improving the performance. And we see that the orange line is the learning the reward, and blue line is learning hyperparameters. And this is soft actor critic, and this is PPO. That we're more likely to get better performance sooner going for the rewards in these complex environments. So that's actually very encouraging and kind of gives us evidence to say that evolution seems like determine internal rewards that enable, or intrinsic rewards that enable agent to learn the task that motivates the agent. And reinforcement learning learns that skill. And putting the two together, we get better policy with less engineering. And we apply these to all these environments in different robots that come, legged robots, car robots, and whatnot, that have actually very, very different motion between all of them. So that's exciting. And we think that this is the most basic navigation skill, being able to robustly go from A to B short distances with respect to your sensors, with respect to your kinodynamics, right, and to your body shape. So the question then is, can we do, what is a long-range navigation skill? And to give you an example, what I mean here is, say you're at home and you now want to go to a grocery store. You're probably going to plan your route something like, oh, I first need to get to the door. Then I need to get to next intersection. Then I need to turn left that intersection. And we can call this a sequence of feasible waypoints or sub-goals that lead to the goal. So that is the planning or longer navigation skill. So planning is then search over that continuous state space. You can imagine that in this kind of multidimensional or continuous space, a plane or whatnot, that now I need to propose somewhere these sub-goals. Where these sub-goals are going to be placed, it's really not clear, right? And then even if we have them, we can sample them randomly, for example, and then we need to kind of connect these into graphs, maybe do the most promising ones, and then we connect them and we have navigation graph or tree. In this connecting step, we're kind of testing whether we can connect, say, this point with this point. That kind of requires rolling out the simulation, which is computationally expensive. So how we can go about this? So one of the standard ways that we can go about this is called PRM-RL. We have an agent that is pre-trained with this basic skill that can go from A to B. Then we can give it a map of the environment. So this is a map of a building. They're both Google buildings. And then for that map, we can randomly sample points to connect to create a graph. And then for any 2 points on that graph, we can roll out this policy or the agent and try to see whether that the agent reaches the other point. And since this is stochastic setting where there are noisy sensors and whatnot, we need to basically do a Monte Carlo rollout 10, 20 times and only keep the edges that that agent can actually successfully navigate for. So when we do that process, we have this navigation graph, which is called PRM, which is probabilistic roadmap, and RL stands for the agent that actually navigates as a local planner between the nodes, and we can reuse it. We can reuse it to ask a query. Say if we're going to go from this side of the building to this side, we take a graph, we do a search for the graph, we have our waypoints, and we go from there. So nice thing about this graph that's kind of has the built-in local policy with the Monte Carlo rollouts, that it will only connect the nodes that that robot can, or that policy can go between. So for example, here, it does not connect these two nodes. And the reason is, it's hard to see in a picture, but if you're actually in the building, there is a pillar here. And this particular robot is very noisy. It cannot fit through this hole. So if it cannot fit in this hole, these 2 points should not be connected. But it nicely navigates along this corridor and so on. And we can compare the performance. Blue line is simulation, and orange line here is on robot. And we can see that the method performs pretty, like the sim to real gap is closed. That means we can start training and evaluating all our things in simulation, and we know what kind of performance to expect on the robot. However, it's not cheap. Doing this naive approach, it takes about 100,000 edge connection attempts and kind of produces very suboptimal paths. There's zigzags. And this kind of rollout step is expensive, as I said. So the question then is, if we already kind of sample these candidate waypoints or the nodes in a node, can we narrow down and be smarter about which one we use to connect? So back to the original slide on how people do this. We practice our skill, we reflect on it, and we get better. For example, if there is a wall in front of me and I'm driving a car, I know that that's going to be harder than turning left or whatnot. And I don't need to go and execute that motion. If I connect sensing with the outcome, I can estimate the difficulty of that motion. So this is what we're going to do. We're going to practice our policy in simulation, going between A to B's and so on. We're going to observe the sensor information and the metric of the interest. So for example, how long did it take me to complete this task, given the starting sensors and the goal that I was trying to, and so on. And I train the predictor based on that. And once we have that predictor, once I'm in a very new environment that I haven't seen before, I'm going to use that predictor to filter out my examples to make them to only attempt the most relevant ones. And things, metrics of interest are feasibility, safety, or the importance of the samples. So this is basically the same thing we're saying. We have our observations for the robot. We have our actor, which is the lower level policy that controls the robot. Robot interacts with the world, collects some experience, and then our planner is connected with the observations, has the task goal overall, and has the predictor model, and proposes the sub-goals for the actors. So I'm going to now look through 3 different planning tasks and predictor heuristics that we can learn. So first one is one-time exploration, and the metric here is reachability. Second one is the roadmap planning and the state criticality. And the third one is multi-agent approach. We're trying to predict and learn teammates' behavior. So for the reachability, the intuition here is, for example, a car is a system with kinodynamic constraints, which means that I can't just move it in any direction. So, example, parallel parking. There's only very few points here that this system can move. And if I knew what these points are, then I can filter out very large number of them and just focus my search only on feasible motions. So this is what we're going to do. We take our policy that we have pre-trained, we execute it a number of times, we observe the sensors and the time it took us to reach the goal. We trained it as predictor. Now that tells me that given my sensors and goals, it's going to take me this much time to get there. And this is the overview of that picture. So if this is my goal, and you can interpret this for this goal, these are all starting positions, and black means short time and white means long time that it's going to take. So if I'm going from here, it's going to take me a long time to reach this point. It's not accurate predictor, however, it's good enough. It's good enough in the sense that all these points here are reachable, and that's all I need to know. And then if it's too conservative here, well, who cares? And then once in the menu environment and I have a sample, I can just go and filter them. Yeah. So how to use it. So I'm going to filter down to only feasible with that predictor, and I'm going to connect them. And this is the comparison. The blue is the baseline method that does a lot more exploration. And green one is the proposed method that is very kind of focused on the samples that it selects. And then we use Auto-RL as a control policy to run it. And here is an example of how it builds the exploration graph and produces paths that are smoother and up to 4.5 times shorter. And the motion planning also speeds up more than double. And here is a video. We see that on the left side, the motion is much smoother. So the second one is the roadmap planning. And here the idea is that we want to learn the criticality. So this is an example of the roadmap in a space. And the most optimal roadmap in a space has the minimum number of nodes that connect any point to any point in that space, right? So the idea here is, can we start with a suboptimal one and learn what samples are more important than others? The intuition here is that these important samples, and we'll kind of figure out what the important samples are locally recognizable. And what I mean by that through intuition is, if you're in a room and you need to go to a grocery store or you go to the airplane, odds are you're going to go through a door, right? And the reason you're going to go through the door is because that is a point in this space that's going to get you to a position where you can kind of explore more. It's also feasible to you. You're not going to go through the window or to a mouse hole because you can't quite fit there. So this is the intuition. Can we learn then these critical space spots? And the way we do that, we build these PRMs just like I described earlier. Start with a suboptimal one. This is 4 Google buildings connected together. And we basically solve a bunch of problems through them. We traverse, go left, right, and see what's going on. As we're practicing these skills, we keep track of each node on that map here, how many times we visited that node, and if I remove that node, does the connectivity of the space break? And if I visited that sample many times and it's critical in that sense, then it's very important. And we then associate the small neighborhood of that point with the score that we assigned, in this case, to the node. And that becomes our training data set. So here in this example, we see that the hallways are super important. And then these points here in the corner, who cares about them? And this actually matches the intuition that we would expect. What are some of the critical points in that map? Okay, so how do we use that? So if I'm now in a new environment, I can, again, randomly sample my nodes, and I can estimate for each node its criticality, right? So this one's going to be important. These are less important. These are kind of eh. And I'm going to go and filter a bunch of them. Just remove a bunch of unimportant ones because who cares? And then these that are super critical, they're going to become my hubs. So these less important ones are going to be connected only locally, but these more important ones are going to be globally connected. So this is exactly what I said there. And the result now is much more compact roadmap. Once I have the map, I can start initial and can traverse and complete the path. And we see here several examples for different robot geometries and motions, how these are the sub-optimized, the uniformly sampled roadmaps, and here are the resulting critical ones that actually get 100 times improvement in the size of the roadmap. And then on the navigation setup, this was our training set. And then in a new environment, these are new buildings that we haven't seen before. The system kind of predicts what are critical samples on this local neighborhood. And it matches, it recognizes the hallways and the intersections, as you would expect, some of the critical points here in the corners, less so. And here is a video of that. So on the left, we have a uniform PRM, and on the left, we have critical, and the resulting path is shorter. This guy is still kind of going around in circles, collecting weird waypoints, while the right on the guy is much faster. And then the last thing I was going to mention is the multi-agent problem in predicting teammates' behavior. So in this case, let's say we have a team of 2 agents, and they have a shared objective. They want to meet in the middle somewhere, but we don't know where and when exactly they're going to meet. And each agent can only observe their own sensory information, right? And they can observe where the teammate is, but they don't have access to what the teammate is planning to do or what teammate's sensors are and whatnot. And each robot here has its own point-to-point or basic behavior policy, like we discussed earlier. And we want to basically generalize this to new environments with obstacles. So one way we can go about this is to have a hierarchical approach, that we have 2 policies. The lower level policy is our basic behavior policy, and then that takes a goal and then produces actions to drive agent to the goal. And then the top policy here produces the sub-goals. Now, the objective for this one should be basically joint objective function based on the expected behavior of all robots in the team. So this is exactly what I said. The low-level policy takes the LiDAR and goal relative to the agent and outputs the controls. And then the top-level policy proposes number of goals. And then each of these goals, it evaluates how valuable the goal is with respect to what Fi is my agent, basically my model, and then Fi minus 1 is for all other robots in a team, what that robot would do. This is exactly what I said now. These are the predictive models of, okay, given my pose, what I see, and my LiDAR, and where my goal is, what is my next goal, and what is my next sensors. And then Fi minus 1 is given other robots pose and what I see, my sensor observation, and where the goal is relative to me, what the robot's pose will be in the next time step. And the reason these models are important, again, like if I see if I see that there is an obstacle in front of this robot, then I know that it probably won't go straight. Or if I observe enough of its behavior that I know doesn't have very robust policy, then I can kind of have some expectations and I can adjust my expectations when I'm planning. So having this policy would be really nice. So how do we train them? So we go and basically randomly initialize the training environment. This is a training environment. And we start both policies, my policy and the other agent's policy. We randomly place the obstacles, initial poses, and goals. And then we observe my sensors and teammates' poses and goals. And we train these two methods. It's basically a self-supervised method. And evaluated in this environment, which is different from the one we were training. We see the loss here. It actually trains as we expect. We're better off predicting our own behavior than the teammates' behavior, given that we're doing this with the sensors, with our sensors, that's expected. And then we use this to kind of propose the goals that are evaluated with respect to the agents. And I'm not going to go through the algorithm, but here's just an illustration that we're going to quickly go through. That we have here, this robot is imagining what this robot would do and creates a set of, starts with a middle point and samples number of goals. And for each of these goals, it evaluates what is their value. So for example, for this goal, it kind of predicts that this robot might go here, this robot might go there, and for this goal, it might predict that I'll go here, and this guy is going to go here, and these two are the top scoring goals. So then it's going to go and narrow down the search, and then basically repeat the process until it thinks, well, this is the best rendezvous point between us. This is this guy thinking. So then it's going to move with respect to that. Now, this guy is going to do in parallel basically the same process, imagining what this guy is going to do and maybe propose this point. And that's how they can kind of go and keep getting to each other. So these are just basically learning curves compared to the MADDPG, which is the multi-agent fully reinforcement learning model. And we can see that basically our method brings the robots much closer together than the baseline. And here is a video. So when there are no obstacles, actually both methods work just fine. This is the baseline, MADDPG. The moment we add obstacle, we see that proposed method is working. MADDPG cannot avoid the obstacles and cannot find the goal. Here they're going around the couches, and sorry for the jinky video, the baseline does not. Okay, so we looked into how to connect sensing and acting with the AutoRL, and it brings better policies with less engineering, and it bakes in the robot dynamics and sensors. Then we looked at how to connect acting and planning by practicing the skill and learning these predictive models, and then learning to estimate these metrics, and then baking that into planning by connecting sensing and planning to have faster and more efficient long-range planning and navigation that's within robot abilities. What's also really nice is that we saw that genetic algorithms or evolutionary algorithms, reinforcement learning, and self-supervised work together to produce this navigation stack. And what's nice about this is that as we kind of improve and have better RL algorithm or self-supervised algorithm, the whole system is going to get better. But also the planning is going to get better the more data we feed it. The more experience I have, I'm going to have better local policies, and I'm going to have better navigation policies, and so on. And this all happens on real robots in real world. And this is one way we can actually scale up potentially navigation and robotics, especially kind of nowadays, where this seems to be really critical. With that, I want to thank all my collaborators, and I want to thank you. And if you guys have questions, and I saw there were questions on the side. Thank you.
Awesome. Thank you so much for the talk. I'm not gonna bother with a lot of questions because it's really late there, I assume. So,
No, no, I can stay. That's fine.
okay. So, so there's a question: why is it tough to generalize to new objects, environments, in robotics or reinforcement learning? Is it because the rewards aren't formulated correctly?
So the reason it's hard to generalize to new environments is because there's so many environments that typically reinforcement learning is trained on single environment and whatnot. So then the question is, what are the training data that the robot is exposed to? It needs to really represent the world, and that's hard. The second reason is, even for the single task, and this is kind of the reward question, the reward uh, for more complex tasks. So the theory of reinforcement learning tells you that the reward should be sparse. You shall only reward the agent when it gets to the goal. However, if the poor agent needs to kind of explore and never finds the goal, it's never going to learn anything. So this is where kind of reward shaping comes into play.
Okay, right. So the next question is: how optimistic are you about hybrid techniques that combine classical motion planning methods with machine learning to increase generalization to real world scenarios?
I think there's definitely a direction to go, and there is a. I mean, this is one example. There is a bunch of other work on, say, using the classical controls and optimal and adaptive controls as the models the for controlling the robot, and then using self-supervision and whatnot to propose the goals and so on. The I mean, these are all great approaches. One thing that's really exciting, that I think is very underexplored area, is using building upon the theory, because control theory has a very rich theory and theoretical safety guarantees and whatnot that machine learning lacks, and figuring out how we can kind of basically align machine learning and control theory from the theoretical perspective. I think it's very largely underexplored area.
Okay, awesome. So um, there's a question which says, could you elaborate a bit on the rewards learned by evolution? Are they evaluated during the evolution process on basis like interpretability or expressivity, or just in terms of the agent's performance?
So in this case, we for when we're training the evolutionary agent, we're only evaluating it based on the uh, performance, the task completion objective. When we're evaluating for kind of research perspectives, we're looking at the robustness on if we increase the localization noise and the dynamics noise and a whole bunch of other things, or dynamical objects and whatnot, to see how resilient the policy is. But for the purposes of training the evolutionary agent, we're just going for completed the task or did not.
Okay. All right. So regarding the kitchen exploration, there was a question which says, was the map of the kitchen designed manually? Could we use a SLAM-based map generated through exploration for same purposes?
So the kitchen example is completely without the map. Because for these short-term goals we don't need a map. the
Right,
it's
right.
the idea there is that if I tell you that the goal is 15 meters to the right, you should be able to figure it out. And if there is a wall around your way in front of you, you should go around. For the PRM methods where we're using the map, we were using both SLAM maps and we were using the images. We actually got better performance building them on top of SLAM maps because SLAM maps are noisy. So that's the noise that's kind of exposed to the robot. So we won't have like corner cases where SLAM is inaccurate.
All right, all right. Okay, so um, I think there are a few recruitment questions on Google AI. Did you want to take a stab at that?
Yeah,
Says-
sure.
So it says, what does Google look for in terms of qualification, publication to do research in AI?
So there's a AI residency program that is annually open. It's fairly competitive, and it's aimed in basically building new AI researchers and creating more. We need more AI researchers across the globe. So applications for that are in January. Uh, Prior AI and machine learning experience is not necessarily required, but it's needed. Ability to do research or willingness to do research is needed. So that is one way. Uh, Prior, so grad school. Other than that, so if it's not internship of the AI residency, uh, PhD helps. PhD in machine learning or robotics uh, does help, and solid publication record in top conferences.
All right. I think there are a lot more questions, but I think
Okay, I'll go through
fair.
them now and start answering them.
Um,
But
okay,
yeah,
so
questions. Go ahead.
yeah, so maybe we can do a few because we're running out of time. So, how much of the policy architecture is inspired by biological neural architectures?
Second.
How much of the policy architecture is inspired by biological neural architectures?
Actually, it's none. We were doing very simple, just kind of shrinking the size of the layers. In this case, and part of it is that is, by the way, very new area. Neural network architecture search for reinforcement learning. I think there is one or two papers right now on that subject. And the reason is reinforcement learning on its own is very computationally expensive, and neural network architecture search is very expensive. So you combine the two, and yeah, it's hard.
Right, right, right. Okay, so there's a question on the simulation framework that was used. Was
Mhm.
it uh, why did you try ROS or something else?
So robot runs ROS. The simulation environment we used was either Bullet for the multi-agent system and PyBullet, and then for the robot navigation, the one where I showed that it's kind of maze-like environment. That's actually something we built in-house, and it just simulates kinematics of the robot. It takes a map, grows the walls, and then takes the kinematics of the robot and runs it around.
Okay, awesome. All right, I think we're going to skip the other questions because we're running out of time. Apologies if your question wasn't answered. Um, okay, thank you so much, Alexandra, for uh, doing this session, especially because it's very late there. And yeah,
No worries. Thank you. My pleasure.
okay.
Bye.
Bye.
Okay, and the chat's gonna stay here so I can answer the questions, right?
Hello. So I think there's some issues with Sharat's like mic, but we'll be shifting to the new session. So uh, right, am I audible actually? Hello. Yes. So we'll actually be shifting to the new session because we've actually got another one. Um,
So I need to close it, or
yeah, I guess we'll handle it from here. That's fine. Thank you very much for
thank
speaking
you.
at Arima. Yeah.